Now, last section. This is similar but different. So here we are trying to determine enthalpies of reaction from something called Standard Enthalpies of Formation. So there's a big long equation for this, and you have to remember it. So standard is what is represented by this little 0 degree symbol here. That means standard conditions, and we'll talk about that more in a little bit. But here is the formula for how you calculate this. There's going to be a lot of symbols that look really scary. It's not that hard, but just bear with me. So what you do is you take the summation, which is a big Greek capital, funky looking E. So that means you add up. Probably Thursday. I'll probably have them both do Thursday. Like Thursday evening, maybe Friday. It's not really going to be a big short turnaround time. And that way we have all of our class time. It's a good question, Sarah. We'll have all of the class time. That way I can help you. I can work through some more examples. We can talk through issues, because this is not intuitively easy. So you have, just write this down. This is a subscript P times delta H with the 0, F for formation, products. That's the key word here, products. And then you're going to subtract. Same thing again, big delta E, N sub R, delta H, degree symbol, F for formation, and here's the key word, reactants. All right, so in this case, N equals the number of moles, just like in gas laws. N is number of moles. So we'll get N represented by our coefficients in our balanced equation. So it means number of moles. All right, so what that means is we're going to do, you look up the delta H's, they're always going to be given to you. They're going to be in a table. So you find the table for each one of your products, you find how many moles it is, and so you do that and you add them all up. But the key thing here is you do products minus reactants. So make sure you remember that. And the way that I remember that is P comes before R in the alphabet. So alphabetical order, products before reactants. When we write equations, we take reactants and we make them products. So this is backwards from writing an equation. So make sure you get the order. Order matters here. Products minus reactants. That's what you got to remember. And these are always for elements in their standard state. For elements that are in their standard state, which means how they exist in nature, it doesn't cost any energy to form them. So what you'll see in the table is your heat of formation is 0. That makes the math way easier because it doesn't matter how many moles there are. It's 0. So you have less to add. So when we use our standard delta H of formation and we're trying to calculate delta H for reactions, we're going to get the same answer that we get using Hess's law. It's just a different method, depending on what you're given, depending on what the question asks you to find. So you're going to use your standard delta H, and we're going to calculate our delta H of reaction. So here's what we have to remember. Heat, Q, and enthalpy, delta H, they are temperature dependent. A-T-U-E-R. All right, temperature, can't spell, dependent. So we measure it at what we call standard conditions. So that would be like STP. We've already talked about standard conditions. We did that with gas laws. So standard states, if you have a solid or a liquid, that would be 25 degrees Celsius or if you prefer 298 Kelvin. Temperature is always 25. If you have a gas or if you have a solution, not a pure liquid, pressure is 1 atmosphere. If you have a solution, concentration is always expressed as molarity of 1. Now, we're not going to be doing anything to manipulate those until you get down to Gen Chem 2 in 180. We'll be dealing with those and manipulating them. So, now, our standard enthalpy of formation, which is delta H, remember this degree sign, that means standard conditions. That means the enthalpy, heat, ultimately, change when 1 mole of a compound is formed from its constituent elements in their standard states. That's a lot of words, and it doesn't seem like it makes that much sense. But, so, heat of formation, so you add up your moles. In this case, it's going to be 1, so you don't really have to include that. Heat of formation of the products, so that's going to be your gold compound, minus, when you add up, delta H of formation of the elements that make it up. So again, products minus reactants. In this case, the reactants are elements. So this is how you build a compound. We won't be doing too much of this because we have a table where it's already done for us. But again, still think products minus reactants. Make sure you remember products minus reactants. All right, let's turn the page. On to page 15 now. There we go. Delta H, heat of formation, standard states for elements. So if the elements are in their standard state, it is always 0. That makes things easy for us. Now, there is a table. It's on page 276 in the textbook. I have a printed one right here. I just printed it off before class. So what I want to show you on this right now is elements that exist as they are in nature. Here is like bromine liquid. Notice this is how it exists in nature. It's 0. Calcium, solid calcium, that's how it exists in nature. It doesn't cost any energy or heat to form it. Graphite version of carbon, 0. So you have to make sure when you're looking at these, you pick the right ones. And even if they're 0, so like the gases, H2 gas, N2 gas, oxygen O2 gas is 0, but look, make sure you don't look at O3 gas because you can pick the wrong one, so just be careful there. So if they exist in how they are in nature, it's 0. We'll be using this shortly. Now, when you look on here, there are several forms of the solid carbon, which is what I pointed out here, solid carbon. So there's graphite and there's diamond. The one with the delta H0 is the one that is graphite, which also happens to be cheap. Diamonds are not cheap. And then we looked at oxygen. Oxygen, you have O2 and O3. The standard state one is the one with 0. So that would be the O2. Or you can call it the diatomic gas, so O2. Okay, now this chart, I do not like this chart. It doesn't make a lot of sense to me, but some people are extra visual and they really like this chart. So if you like this, I think it's a little crazy, but now, what this says is first you have to break things down. You want to break everything apart, which is, so these are our reactants. So we have to break everything apart into its constituent elements, and then we're going to start making new compounds, and we're going to make energy or give off energy that way. Again, this looks way too busy for me, but I don't like it. So here this says, what is the standard enthalpy change for the combustion of methane? So we're going to blow up some methane. So if we know the heat of formation for the compounds, we can subtract how much it costs to make our reactants, add the cost of our products, and get the difference. So again, it's always products minus reactants. All right, so the first thing we need to do is we need to balance the equation. All right, so when we balance the equation, let's look at this is a combustion. So I'm going to do carbons first, 1 and 1, hydrogens 4 and 2, so that needs to be a 2, oxygens 1, 2, 3, 4, 2, there we go. You can put the ones in if you prefer. Now, so what we need to do here is we can look on our chart and, oh, this one says do it the long way. All right, I'll do it the long way. Let's break apart methane. So methane, when you have CH4, that gets broken down. So heat of formation of methane. What it costs to make that, that's 1 carbon and 2 hydrogens, right? Yes, so that makes CH4. So again, when we're doing this, we're going to do products minus reactants or the elements. So add them up. Products, negative. On our chart here, if you look here, methane, negative 74.6. And all this is in kilojoules per mole. So when you're doing these numbers, these get really long horizontally. What you can do, if you want to, is leave your units off, but make sure you remember to put them back at the end. I try to go ahead and do them as I go along, but just be careful because you do need to have units on this. It's not a ratio quantity. So delta H, yes, you'll always be given a chart. You do not have to memorize these. So remember, kilojoules per mole. All right, so methane, negative 74.6. All right, so how many moles of methane do we have? 1. So we have 1 mole of methane, negative 74.6 kilojoules per mole. There we go. And then we're going to subtract our reactants here. So we have carbon. Since it doesn't specifically say diamond, we're going to say carbon, that's the 0. So the way I do that is I'll put 1 times 0. That makes things easy. And then we add up 2 of the hydrogen. So put your 2 moles. Always put your moles first. So, and then let's look at, for hydrogen, on here, hydrogen, H2 gas is also 0. Well, that makes it easy. So this is all zeros. So we don't have to subtract anything. So this becomes negative 74.6 kilojoules. I guess we can say per mole if we want, for methane. Now, the rest of these, so that's how you would break it apart for that. Now, these were from elements. Moving forward, notice if it's already on the chart, You don't have to do that. So that was an extra step. It was basically wasted. If it's on the chart, you can just use what's on the chart. So let's look at oxygen. So heat of formation of oxygen on the chart is 0. That makes things easy. Kilojoules per mole. We'll keep units in there. Now we have heat of formation of CO2. So find CO2. Again, you got to be careful when you look at these charts. Make sure you're looking at the right thing, because it's easy to get these mixed up when you're looking at the wrong line. So negative 393.5. Negative 393.5 kilojoules per mole. And then H2O. So let's look at water. Water's another one you have to be careful with, because look, water is on here twice. It's water gas or water liquid. In this case, let's double check. This is water as a gas. So water as a gas, negative 241.8. So negative 241.8 kilojoules per mole. Now, as you go along, you don't necessarily have to write all of this. You can just start with your summation, but this is kind of the information that you're going to need. So if it helps you to write out each of these and look on the chart and get them before you plug it in, go ahead. Otherwise, if you just want to start plugging and chugging, go right ahead. So now let's do our big summation. So we're going to have our summation. That means add them up. Add them up. Moles, heat of formation of, remember, products always come first. Products minus, add them up, number of moles, heat of formation, reactants. All right, so I tend to use brackets on these because I'm going to have brackets and parentheses, and I tend to get unorganized or confused putting things in the calculator. So when I work these, I tend to have a lot of lines. Some people can put it all in the calculator at one time. Great. If that's you, fantastic. All right, so we want products. So let's look at our products on the side. So in the equation, remember, these are the products. So let's write that. These are the products on the right side. These are our reactants on the left side. All right, so we want our products first. Our first product here is CO2. So I'm going to put a bracket. How many moles of CO2 are in our balanced equation? 1. So 1 mole. Heat of formation of CO2. You can look on the chart now, or we already wrote it down. Negative 393.5 kilojoules per mole. Now, this is where the summation comes in. We have another product. We also have water. So we add it. Plus, we have 2 moles of water. From the chart, we get negative 241.8 kilojoules per mole. All right, do we have any more products? We have done CO2, we have done H2O. If it helps you to do that, so that's CO2, that's H2O. Write it on in there if you want. That's all the products. Now I will close my bracket. Now we're going to subtract. We're going to open a bracket, and we have to do our reactants. So reactants are up here on the left. The first one is methane. There's 1 mole of methane. And methane is negative 74.6 kilojoules per mole. We're still in the summation part, plus oxygen. So 2 moles is 0, so we don't have to worry about that, kilojoules per mole, but I always include it just so I remember. All right, so now we can do a unit check, cancel out the moles. So our final answer here is not going to have any moles in it. It's just going to be kilojoules because we've canceled out all the rest. So order of operations says do parentheses and brackets first. So I'm going to do that. I'm going to go through and multiply. So 1 times negative 393.5 is negative 393.5 kilojoules. Now, since I'm adding, I still say plus. This is how I do it. Again, how you do your basic math is up to you. Now we need to multiply 2 times negative 241.8. So let's do that. 2 times negative, I already forgot, 241.8. Negative 483.6. So negative 483.6 kilojoules. Done with that. Now I'm going to go over, work on my reactants. Same thing. 1 times negative 74.6 is negative 74.6 kilojoules. Moles are gone. 2 times 0 is 0. You can write that if you want, but we're done there. Now, keep working inside the brackets. This one still needs some work. So I'm going to say negative 393.5 plus negative 483.6. Again, if you just prefer to do subtraction, great, do it. But that's going to give me 877.1 kilojoules minus negative 74.6 kilojoules. Again, you have to be careful here because you're adding and subtracting and multiplying with negatives. So be very careful where you push your buttons on the calculator. So now I have, that's a negative. See, I forgot to write it. Negative 877.1. So that's still here. I'm going to say minus negative 74.6. There it is. Negative 802.5. Negative 802.5 kilojoules. All the moles were gone because we used a balanced equation. This is the final answer. Put a box around it. So depending on what you prefer, I have some students that when they have their equation, they go ahead and look on the charts and they put their delta H's for each one of them above that, and then they plug and chug. I have some people who just start with plugging and chugging. I have some people who like to make the list before they do it. It doesn't matter. You pick the method that works the best for you. All right? So let's turn the page. Look, it's the last page. So, what you had asked me about, will you have a chart? Yes, you will always have access to a chart. A lot of times I'll end up copying and pasting parts of charts from out of the back of the book. There's a huge list in the back of the book that you can use. It's one of the appendices. Because here it'll say from Appendix 2B. Yeah, that's where you find it in the book. So you can find it on the e-text as well. When you look in that, I don't have, here, let me grab my book. Appendix 2B. Or not to be, that is the question. So be careful here when useful data, standard potentials. Here we go. So when you look at these in the back of the book, you have to be careful here because you're going to have, it's going to give you multiple things. It's going to tell you what the compound is. So make sure you look for, you find the right one, whether it's a solid, a gas, solution, whatever. These are in order according, they're in alphabetical order according to the first element. Now, these are thermodynamic properties. So there's 3 different columns. The one we care about is delta H heat of formation, and it's in kilojoules per mole. So make sure you're only looking and using information out of the first column here. So don't use delta G, don't use S. So, and make sure you use the correct units here when you're looking at these. And again, you may have to do that on some of the ones for the homework. Now on a test, I'm not going to give you this pages and pages and pages of all this. I section it out and I'll give you those. You might also, because I'm not sure if on all of them you can find everything you need from this chart that's in the chapter, but you might. So if you want to use the back of the book, it starts, oh, it's in an appendix. It starts on page A5 is the page number if you want to look at that. But it is helpful to know that it's there. But here for this problem, it's mighty handy. They went ahead and just summarized it for us. So I like the little summary. So here we have 4NH3, 5O2 gives us 4NO plus 6H2O. So here is this example. So again, write our equation so we don't get lost and we know what to fill in. So in products, moles of products, heat of formation of all our products, and then we're going to subtract when we add up moles of reactants, heat of formation of all our reactants. So remember, products before reactants. That's the key part here. Now, some people, I'm gonna do it this way, and you can decide if you like it. Look at your equation. It says 4NH3. They find NH3, and they're gonna put negative 45.9 above it. O2, they'll put a 0. NO, positive 91.3. Water, negative 241.8. So if you like to do that, if you like to get oriented that way, please do it. If you don't want to do that and you just want to jump right in, go for it. Now, just remember to start on the correct side. Start with products. So here we're going to add up. Start with a bracket. Open bracket right there. Scoot my paper up so you can actually see it. So here we have an open bracket. And 4 moles, because I'm starting right here, starting with my first product, times positive 91.3 kilojoules per mole, because that's what it says in the table. Those are the units given in the table. So do double check your units. Moles are going to go away. Summation means add them up. So we're adding them up. When we add up, we're going to add our other product. So that's 6 times negative 241.8, also kilojoules per mole. And now I'm done with the products. Subtract. Now let's work on the reactants. So let's go to the left side. Open your bracket. 4 moles times negative 45.9 kilojoules per mole. Moles go away. Moles go away. Should have done that over there. Plus, I don't have a way to additionally focus the webcam. That is a known problem. It doesn't have a way to adjust it. But I am also recording on the phone, so that does record in better high def. I'm working on some experiments that if we can have to continue this after spring break, maybe it will be in a better platform. But unfortunately, this is what I'm stuck with today. But that's a good question, and I do understand. I've had to do this on the other side as a student as well, and it's no fun. So I finished NH3. So, and now I need 5 moles of oxygen but it's 0, so it's going to go away. So moles go away. Work on down. Now let's work inside the parentheses here. So I'm going to have 4 times 91.3. So that's a positive 365.2. Moles have gone away, so it's kilojoules. To work on the water now, plus, there's a decimal in there, 6 times negative 241.8. So that's negative 1450.8. Moles have gone away, so it's kilojoules. Done with that one, close the bracket. Minus, open the bracket. Work on this other side. 4 times negative 45.9. Negative 183.6. Negative 183.6 kilojoules. 5 times 0 is 0. I'm not going to bother carrying that down, but you can if you want to. All right, continue to work inside the brackets. So on here I have 365.2 plus negative 1450.8. That's not a times, that's a plus. All right, so that gives me negative 1085.6 kilojoules minus negative 183.6 kilojoules, because that's all I have left on that line. So I'm just going to carry it down. So if you're somebody that wants to say minus minus is plus plus, then do it. But I'm going to say minus negative 183.6. And that gives us negative 902 kilojoules. That's the final answer. That might be better. Last one. Hey, and then we're done. Then all I'm going to have is an open classroom for the rest of the week where you can work on these and then turn them in when you're done with that. So here, this is how the question will say. It will say use standard enthalpies of formation, or it will say here's this reaction, here's these equations, and you have to use Hess's law. So if it says standard enthalpies, you get to use this. A lot of people find this way easier than Hess's law, because as long as you can remember products minus reactants, you're good. But if it gave us a whole bunch of equations that we had to manipulate, we would have to do Hess's law. All right, so I'm going to work this one, and I'm just going to jump right in. So again, this may be your preferred method. If it's not, then that's okay. So here we're going to add up. Here's our equation. So these are our products, these are our reactants. Products first. So let's add up 1 mole of aluminum oxide, Al2O3, which is negative 1675.7. Units are kilojoules per mole, so the moles are going to go away. We do have a second product, so let's add it together. There's 2 moles of solid iron. Oh, that's how it is in nature. So that would be 0 kilojoules per mole. That makes things easy. Done with our products. So if you want to write Al2O3 up there, Fe up there to help you keep track of it, great. I need to scoot the paper up because you can't see it. There we go. Now, keep going. Let's look at the reactants. So subtract, open your bracket, 2 moles. First thing we have is aluminum. Oh, that's a 0. That makes things easy. but I still always include it on my front so I don't miss anything or forget about something later on when that's not the case. Plus 1 mole times, that's iron 3 oxide, negative 824.2 kilojoules per mole. All right, so moles go away, moles go away. We're only in kilojoules. Close the bracket. Now, carry it down. Let's work inside this bracket for now. Some people prefer to work on one side and then the other side. That's fine too. I just work one line at a time. So 1 times negative 1675.7 kilojoules plus 2 times 0 is 0. Don't need that. So we're done. Minus 2 times 0 is 0. So you can put a 0 or you can just leave it. Negative 824.2 kilojoules because the moles went away. All right, so now we just need to subtract and use a calculator. So here we have negative 1675.7 minus negative 824.2. So I get negative 851.5. Final unit is in kilojoules. And that's it. That is the end of thermodynamics.